Okay, so let's say that we have an infinitely long current carrying wire with current flowing out of the page, but with a value which is changing with time according to this expression. So let's say that A is some positive number, and so is I naught. And so the current is increasing with time exponentially. So forget about how we can generate that. It's just changing with time. So now we imagine having a rectangular, let's say we have a rectangular loop of dimensions W and L, and we place it right where it is there. So it's actually lying in the plane of our sheet of paper. And let's say we want to find the EMF. All right, what's the EMF induced in this rectangular loop? So we know that we first need the magnetic flux, and then we want to take the time derivative, or rather the minus the time derivative of the magnetic flux, and then we'll get the EMF. So let's get a sense of this. Right, so the first thing we want to do is evaluate phi b, which is, well, by definition, the integral of the magnetic field over the surface. And so this could be the area over which we integrate, the rectangular area. So the dAs are, say, pointing out of the page. So let's maybe draw a dA right here. Let's draw it in red. So dA here is pointing out. Right, that's an infinitesimally small area with a direction out of the page. And let's make the magnetic field blue. So, right, the current is coming towards us, and so it has to circle around by the Biot-Savart law. dl, say r hat this way, would point downward, right? So the dl is pointing upward, r hat is pointing to our left, and the thumb is pointing downward. So it's telling us that the field here is pointing that way, the field here is pointing that way, and so on. It's circling around, but we need the field at the loop, so we need the field here. So here the field is going to be a little bit smaller, but it's going to have that direction. We made a dA there, so of course we need the field there, which is going to be pointing sort of like that. Right, it's going to come in and sort of circle around. Here we're a little bit closer, so it's a little bit larger. And we could make other field lines over here. Maybe this one's a little bit larger. It gets smaller as we move away, and so on. Field is always circling around. So that's our field. And we could draw a few more dAs, so maybe make some dAs everywhere where there is a field drawn. So the dA is pointing out. And so what we can see is that when we do this calculation, we have the dot product between blue field lines that lie in the plane of the page and dAs that are pointing outward. So this becomes at every point the magnitude of B times the magnitude of dA times the cosine of the angle between the two, and that cosine and that angle is 90 degrees, right? Because the dAs are out of the page, and so we get that we're integrating 0 at every point, so we just get 0. So the magnetic flux is 0, and it doesn't matter that the field lines are getting larger. So in fact, over time, we could draw the field, so the field lines are getting bigger over time. Right here, bigger field lines. That doesn't influence the fact that the flux remains 0 because the orientation and so on isn't changing. And so we always get, despite the increase in the strength or the magnitude of the field, we get that the flux is 0, and so the EMF is asking what is the change in the magnetic flux, but that remains 0, so there is no change with time, and therefore there's no EMF.